because we are going to look at the ESP side of our model. So what we have done so far, we have generated the model, we extracted it, made into a header file, we ported that to ESP32, and it is running, it is producing the waveform. Now my question is, are we doing this job of running on this properly or not? I don't know whether you guys thought about it. What are we doing in the code that I showed you in the lab yesterday, in lab 11 or day before yesterday? We created the header file from here. We attached it with, not attachment, we are linking it with model.cpp. I told you that this is a C++ file. And then the .ino file, which is having the function about the model, actual and predicted. Predict is called here. And actual header file data, the model data is here. And this file is making use of it, accessing the data, all those things. So we have these three files. If you look at the way it has been structured, you know that setup is the entry point for the program to run on ESP32. After that, before that, it does something else, configuring the devices, all those things. But finally, the control comes to us as an entry point to our program using the setup function. It is similar to our main function, okay, in our C. So it comes to setup, then we take control of the ESP32. Now, one thing you should remember, this setup is made to run on core 1, which I mentioned it some time back when we spent at least 2 weeks on how does the multiple cores run and how do we use the FreeRTOS APIs, all that we saw. So we know that the setup itself is a process, itself is a task. Okay, let me call it as a task. It doesn't matter. And which is running on core 1. It is meant to be run on core 1. And what we doing here, we set up the serial baud rate, we set it up. And then we did something else, we printed some data. Then we called loop. Loop is getting called, actually not, we are not calling. After the setup is done, loop is going to be called in a for permanent no while loop, or inside that loop function is going to be called. It is also default done by the infrastructure. So this function is going to be repeatedly called. So even if it is coming out of the loop, no problem, because it is within a infinite loop. Understand? In ESP32, the tasks which are running cannot terminate, in the sense cannot come to the end of the task. We should either kill it or we should be in a infinite loop. Otherwise, you will get an exception that you might have seen it in many places, right? Many occasions when you are writing a code. The major flaw is that we do not, either when we are coming to an end of a task, either we should kill it using a delete task, or we should never come to the end of the task. You should be inside the loop forever in a loop for loop. That is taken care of here, because this loop function, though we put some instructions and we don't say that you go back, it is implicit that it is called inside a for loop. So loop function is called multiple times. It will never come out of this because there is an infinite loop going. So what is happening is, we are calling predict here, if you recall, and then we are also trying to plot the output, and then we keep calling it inside the infinite loop. So what is happening? The whole thing, the prediction as well as the plotting of the data is all happening on core 1, because this loop is running only on core 1. You may wonder what is happening to core 0. Okay, core 0 doesn't have any task other than its own idle task, okay, which is the lowest priority task. will be made to run when you don't have any other application task which is scheduled to run on core 0. I don't know there are some other processes running or not. We have not checked it, so I cannot claim that it is not running anything. But certainly, if we have not scheduled any task, our tasks are only, we have not created even tasks. So what we are running is this loop, which is running on core 1 because the default it comes here. Core 0 we are not using at all from our perspective. It may be the internal driver or some other task may be running, which is not our concern, but we are not using the core 0. Is it a good way of handling multiple cores that you are given with? So remember one thing, the hardware features are available to us. Whether we make use of it is on our head. That depends on the software we write, how we make use of the facilities that hardware provides. Okay, we know that most of the time we buy a mobile with lots of features, hardly we use maybe few of them, maybe 30% or 40%. Most of the features we don't even use. There are many, including the laptop that we have. So it's because of lack of uh, going deeper into it, or maybe not finding time to dig deeper into it. But that is not the excuse to use our hardware that we have. Especially if you are releasing a product out of it, we need to make sure that we make use of all the facilities to our advantage. I'm not saying that because one module is there we should make use of it. If it is needed, we should use it to our best possible extent, because whether you like it or not, both cores are going to be on and both are powered, and it is going to consume power. It's going to be running something which is of no use. So we need to make use of the cores. Now how do we do it? So that is one question we are going to answer today. Now second question, we have two things to do when we are running this software on ESP32. Okay, I am only concentrating on what is running on ESP32. We have two things to do. One is plotting it. Okay, plot the waveform so that we see that output is coming. I will come to the chat window shortly. Please hold on. I have seen that there is something happening. So plot window is continuously plotting some information which we want to see. But if you observe one thing, the plot is also using the serial port. Okay. So plot is one way of using the serial port. Other way of using it is monitor. We saw that also. So far we have been using monitor, where we print some information. This is for human to read in a text form. Okay, textual form. This is the graphical form. So there are two different ways of pumping the data into them. You cannot pump what you do for this into this and expect it to read. You cannot read if this thing is running at a like a Formula 1 car. If it is running, you can't read anything out of it. At the same time, you will get bored to death if it is plotting slowly for 3 hours the one sine wave. You will go mad. Now how do? We want the speed of this for plotting data, as well as we need the slowness of this monitor to observe some things here. How can we do, using our single software, both the facilities? How can you make use of it? That is what I am going to cover first, and then we will go into the details of how to make use of both the cores. That is the next level of details. Now, to do this, we are going to use the technique that I have talked about yesterday, or not day before yesterday, if and def and if def. Luckily, you guys asked me some doubt on this and I could explain it. So if you have followed that, or if you are not followed, if you have gone through it again, yesterday you had a holiday, then you will be ready to understand what I am planning to explain today. Okay, fine. Now let us look at the question coming there. Can we use core 1 for computation and core 0 for plotting or displaying the output? Okay. Now, I will come to that when I am talking about it, because some cores are meant for something based on the design they have done, the Express IF guys. So I will come to that shortly. I am going to talk about it. Okay. Now, let us start off. So what I plan to, the naming convention, what I am planning to do going forward is, because it is, I am releasing so many Python files, so many, now we are going to be seeing so many INO files. You need to organize it properly in your directory structure. Otherwise, I can assure you that you will go totally confused. And in case if you want to make use of anything that we have written in the code in the class, during the exam, you will not be able to do. So I am forcibly making you to structure your course directory whatever convenient way you want. I am trying to do my best to naming them properly and grouping them properly and giving it to you, but you need to structure it. You can follow my way of doing it, but I have much more than what you guys see, because before coming to that class I am at have tried out n number of things before finally deciding on something. So I have many versions, and I myself get confused many times. And I what I do, okay, to you know make use of, or not make use of, because of the lack of memory. Okay, what I do is, in a directory, what if suppose I have something, I default create a readme dot text. Okay, I create a readme dot text and then tell something about myself. Okay, it is to myself. What all is the content of this? Why I did it? Where did I produce it? Any references I had looked at, and which section I plan to do, what exactly this is doing, what commands I gave for installation of this particular thing. All that I captured in a README on that particular directory. So it has the information about what are the files there and what they do. So this is how I manage my experiments with many things. Okay, I leave it to you how you manage, but you need to do that. Okay, now we have serial monitor and plotter, two ways of observing our program. Now my question is, not even question, my, now I'll give you the clarity on why we are doing this. Okay, we have a ESP32, and then only connection we have to the board is the serial port on USB. Okay, please remember it is running on USB. Physical, if you have to draw the OSI layer, physical layer is USB. Okay, the link layer is serial port. Okay, the signaling is USB protocol compliant, and the voltages that you see on the cable will be USB specific, either 2.0 or 3.0, whatever it is. And there is a USB 5 here, physical interface, as well as on your laptop there is a USB interface. So it is talking over the USB interface, but what it is conveying the data is a serial port. So that's why we are very particular about setting the baud rate here. So whatever baud rate you set here on, whenever you open the monitor, it comes up on the bottom. That is very important. What you set here should match with your setup code and the serial you set it up here. This should match with what you show here. Otherwise you will get garbage. The reason is, one side is sending it in some speed. Okay, we are deciding the speed of the data, or how much of data you want to send. If you are choosing 9600 baud rate or 115,200 baud rate, you know the difference between these two. But you cannot expect to read a data which is coming in this baud rate by one side seeing the data at this rate. So if you are seeing this data at this rate, you are going to sample the signal at a rate of 9600 baud rate. So you are not going to see all the bits. So there will be garbage what it sees on the signal. Okay, so that is why you have to match both the baud rate. First thing you should check. Now going forward, it is more important. Do not get jumped to conclusion that your program is not working when you don't see anything on the screen, either monitor or the plotter. The reason is, I am going to change the baud rate now. Okay, so I am insisting that you please pay attention to this. Being hardware, not hardware engineers, you are all embedded IoT engineers. You need to be aware of this. So what you set here, you have to make sure that you are doing it here, because you may be running different program which may have a different baud rate. Earlier I told you not to touch it, but I am going to touch it now for a valid reason. Okay, so this you keep it in mind. Now, why did I talk about it? Okay, this serial monitor is what is conveying the data. So we have only this interface currently to the hardware. Now, what if I want to debug it? I want to debug the code that I run on the board. Okay, the code is running here. I want to debug it. Normally what happens is there will be a debugger. Okay, there are so many JTAG debugger and there is a plenty of debuggers available. There's a hardware available, debugger hardware, which talks to the hardware. This hardware is maybe I call it as ESP32. Okay, so what happens when you want to debug really in your simulator? Suppose you are running a code block or something, you do a step in, step out, block, breakpoint, you do all that. If you do, if it is code is running on the same machine, you can stop the instruction execution and then look at the variables, all that you can do. But that is not possible. Now, I'm not saying it is not possible. It is not that easy if the code is running on some other hardware and your debugger, supposed to be your IDE, is running on some other laptop. Now, the interface matters now. If I have a path like this, a debugger hardware, and then there is a matching debug hardware on the hardware side, on the ESP board side, then what happens is I can actually do whatever I do by running the software here. I can do it also by running the software here. How? I say that I want to put a breakpoint. That means I want to stop the program here. Then what happens is this information is passed through this hardware and this debugger unit is programmed. When the PC, the program counter, comes to that particular address of whatever the user has put a breakpoint, please stop the core. Stop the core, freeze it, all the content, register content, you pass it to me so that if the user wants to see the register content, I can display it. So the debugger hardware, an external entity, as well as the built-in hardware, which is stopping the core and then extracting the information back to the debugger, is a must if you want to do that. But fortunately or unfortunately, we do not have that support here. I will tell you the reason. Because the debug modules will eat up the space of the chip. So it will become expensive because they have to increase the wafer size, increase the pin numbers, count and board. Everything is cost. You cannot get a board for 500 rupees if you want a debug unit to be there. So if you want a cheaper hardware, you need to live with the limitations of the hardware you have. Now what is the limitation? We have only a serial port interface to the board. Laptop is here. I have only serial port interface, though it is through USB, which is very convenient because nowadays laptops don't come with a serial port at all. At least they have taken care of that. So now what we do? I have only one way of getting the data, printf. Okay, our friend printf. But I need it in two different ways. As I mentioned, plotting as well as monitoring. So monitoring, I want to do it in a slow rate. Plotting, I want to do it in a much faster rate. But I use the same printf, serial printf, of course. So if I have to use a plotter, I need to only give some order, okay, some data, and then some tab, and some data, and some tab. So like that, I can give multiple things. So if I am drawing only one graph, I will give only one data. If I want to compare two things, okay, I give two data. If I have to draw one more, I give one more data. So I can actually keep pumping only the data, which can be a floating point data, no problem. But you need to pump only the floating, the data. You cannot write hello world or I am sending this information, please plot it, all that nonsense you cannot say. You need to say only label and then the data. If you do all that, the normal printf like talking to human being, then it will not work with the plotter. That is meant for monitor, where it is for human readable format. So, but the problem in monitor is I cannot print it in the speed I print it here, because plotting can be faster, whereas here I need to print it with a slow speed. How do? I put a delay in my program, delay 1 second or something, so that I intentionally slow it down and then see the output of whatever I want to see. So we need to use two ways of debugging our code because of this reason. Okay, I hope this is clear. Now, how do I make two modes of debugging? Serial monitor debugging, serial plotter debugging. Okay. So what is the monitors use? Output values of variables of interest in a readable format. in a readable rate. Check the values of variables if the program logic is to be debugged. Now I want to see if this condition is coming to that or not, else is happening or not. I want to debug my program. Then you have to be in a monitor mode, and then your loop program or your task, whatever you are doing, forcibly put a delay 1 second or whatever. Be aware of this, that you are forcibly putting a delay so that you are having time to read whatever output is coming. Otherwise, what you should do is print it and delete it or stop it, and then observe it slowly, or plug the board and then look at the output what you got. Anything you can do. That is a forcible way of doing it, but a decent way of doing it is delaying the output what you have. So serial print or println, you can use it for printing output values or error conditions or control flow if you want to debug. But that is not going to be very friendly when you are doing a plotting. All this, remember this, all the outputs that you have done, you are using the same serial print, remember. So that is what is used by the plotter also. So plotter means nothing but what is done on this side of the funds, laptop side. Okay, laptop side is what is looking at the data. It is either going to plotter or it is going to the monitor. So what is coming should be in the format which is compatible or easier for the plotter to plot it or the monitor to put it on the screen. Both can do the output whatever you are getting, because they are all coming as ASCII format only, but it is not going to be comprehensible, it's not going to be readable. So what you should do, you should have some way of developing the code which is common. Okay, I don't want to have a code one for plotting and then another code which is for the monitor. It will be a cause for concern. Okay, you are going to add bugs, you fix some bugs in the monitor, and then when you want to transfer to the code which is meant for plotting, you will make mistakes and these things will break. So you need to maintain one single copy of the code, but enable plot when you want to plot, or disable the plot and enable the monitor. So if you disable the plot, that means indirectly you are enabling the monitor. So how do you do it? If and def is our friend who is going to help us. So plotter is when the model output needs to be plotted at a higher speed to compare with the actual value, to view the shape of the waveform, to analyze the values of by observing the shape of the waveform. Okay, we are not interested in minute details of what exact values you are getting, because you have already debugged them and you are convinced that it is working. Now you want to see a global overall picture of how things work, how fast it works. So you go to the plotter. So these are the two ways of using it, two means of debugging your code. You have to use, these are all called preprocessor directives because it is used by the preprocessor, as I explained. One thing I forgot to mention, I am sure you may be knowing, this hash if and def, or hash define, hash include, okay, it should all be in the column 1. Okay, you cannot give a gap, okay, it should be in the first column. Okay, I hope you guys know it, you are all C experts, but just thought I will tell you. So what you do is define a plot constant, use it for your purpose. That's what I'm going to show you the code. So based on whether you want to plot it or you want to see the monitor, you compile the code. So what I say, when I say compile the code, in a file you will have hash define plot. Okay, hash define plot. That means what? You are defining the plot. Now that means you are interested in plotting output. So you have to put the pieces of code which are meant for plotting under the if def plot. Okay, hash end if. These are all the piece of code you will keep it which are under the plot definition. Now when you compile it, this code, and then download it to the board, when you want to see it, you better choose serial plot here. Okay, if you choose monitor, nothing wrong, you will get some running values which are running very fast. Then you will realize that, oh, I am supposed to choose a plot, and you can come there. I'm not saying that by choosing the monitor the things will fail or something will break or something will explode. Only thing is you cannot see it. So you have to choose plot if you are chosen this. Now suppose I am not getting the way I want, the code is not running properly, then what I do, comment off. build it again. Please remember, you have to build it again. When you build it again, what happens is plot is not defined. So this piece of the code is not going to be included in the compiled output. Whereas if you have put some other code, if and if not defined plot and hash and then if plot is not defined, this part of the code will be included. So selectively adding the code or removing the code, you are doing it with this feature, compiling it again. Remember, you have to compile it again. Don't think that you can just do this and then run it on the board. You have to compile it, build the executable and put it, and then open either plot or monitor to view what you want. So this is how you need to debug your code when the things are running on your board, especially a board which doesn't have a debugger, okay, or the hardware debug module, if I have to be very specific. I hope this is clear. So let me check whether there are any questions so far. Nothing else. Okay. Now, before I go into the optimization portion, let me show the code to you so that you don't forget what I said. So this I have created it. Okay. In fact, I have taken the same code and then made a lot of changes. Okay. So it is keep adding more and more to you. Okay. So let me now tell you what is happening here. I have done a couple of more things also. For a moment, forget about this. Okay. Now I have defined plot when you want to get the output to be plotted using serial plotter. So I have defined it. Now that means the last compilation I did, I enabled this. Once I do that, what will happen is my code, don't look at everything. I have not yet explained. So I have put if def plot. Now this is the label. If you recall, it is coming on the screen, actual and predicted. So I have put it under if def plot. Okay. And then I have done, let me call, I have actually if plot, if and def, these are all if and def, if def plot. So I have put all the plotting function, I have grouped them all, plotting of the values, I put it in the plot function, passing the actual y value and predicted y value. So I defined it as a function, and then I'm calling it under if def plot. So what I have effectively done, if I want to plot it, I have put all the code which are supposed to be enabled for plot, I have captured it there. Now what I am doing on if and def plot, okay, let me now come again looking for if and def plot. That means if plot is not defined, what I want to do, it will not be included. If it is plot is not defined, this is not going to be included. Rest of the code will be as usual, it will be compiled and included. It will look for if def and if and def of plot. Now if and def plot, what is this? If I have not defined plot, that means I am going to use the monitor. So I want to delay it. Okay, every iteration I want to delay it by a second. And then I want to say that, okay, this inference task is running on some code. Okay, you may be getting some clue. Okay, so I am running some task on particular core. I want to print the core ID to verify it, whether my code is running. I have put it under if and def plot, because I don't want this string to be appearing when I am plotting the data. During the plot, I want only the data which I am interested in. I don't want all this nonsense. So I put it under if and def plot, and then added a delay also, because during the plotting, I don't want the delay. I want faster output. So if and def plot, I am entering the task, I am doing this, all whatever you want to add it as a debug statements, you can put it. But your code may look clumsy. I accept it that it will not going to be readable. Okay, you have to be a little bit patient in coding it properly. Like Python, there is nothing restricts you. So you have to have a discipline to write your code more or less, as much as possible that you can understand what is happening. Okay, I have tried my best. I'm not saying that I am the best coder in the world, but I have tried my best to follow the conventions, which you can take it as a first step and improve on it. Plus, okay, I'm not saying this is the best way, but this is what how normally companies or the industry people do. Okay, fine. I am not going to the details of every piece of code because I need to explain you something before I go. 1 second. Anything asking? Okay, no questions so far. Very good. Okay, now I'm going to talk about how do I structure this code for making use of the dual core. While running the neural network model on ESP32, different optimizations can be thought of to exploit the hardware features included, which is including the dual core. When a regression models of waveforms are being run on ESP32, two major activities happen. One is inferencing and the other one is plotting. Now I am calling plotting as a major activity because that is what we have, okay, nothing else to do. We, okay, though I'm not saying that this is a very big operation compared to this, okay, this is really a good thing, okay, we are doing a solid thing. But if you keep adding more stuff, okay, maybe getting that image from Wi-Fi or some Bluetooth communication, and then you can keep exploring, real applications. You'll have more things to do in a in an application. But in our simple case, we are only doing two things. So I want to divide this also into two cores, okay. But actually, running both on the same core is going to impact the performance. I'll tell you why. See, inferencing is going through the whole tree. Okay, it depends on how big your tree is. Doing every arithmetic, okay, floating point arithmetic, and then coming out with the output, right? And in our case, regression model only we are talking about. Now, this much of operation has to be done. It is not a simple job. It's all floating point operations, and lots many operations are being done. And then suppose if you are running it on core 1 only, the plotting also, what happens during the plotting? Let me explain. When you want to plot, what are you doing? You are saying serial print y data and then y actual, something you are sending, right? So because you are sending using print, you are not going to send only a byte binary value. You are going to send a ASCII value, okay? Because when it appears on the monitor, you can see the values of what is being sent. So that means what? Serial port is actually sending you the ASCII values of what you have put in. So it's not a single byte. It's a string of characters. Now string of characters may be some 10 bytes or whatever, 10 strings, okay, 10 characters or maybe 15, whatever, one data value, okay, based on 0.23456 or whatever. Now, how much time does it take for this to go across the serial port? That depends on the baud rate. Baud rate, assume that suppose you have chosen 9600 baud rate, okay, for an example. So you need to, this gives you the time it takes for a particular bit value, okay. This is, the baud is nothing but bits per second, okay. I can call it as a bits per second. Then 9600 bits per second. Then how would you know how much time does it take one bit? One bit will take 1 by 9600, whatever it is. Now, for sending 1 byte of data, 1 byte of data means 8 bits of data on the serial port. It is going to come one by one. It's not a parallel port, serial port. Okay, like this. This is the 0th bit, maybe this is the 8th bit. There will be a start bit and then there is a stop bit. Normally, it is 1 bit or 2 bits maybe, but we'll assume that they are all 1 bit wide, start bit and stop bit, because serial port should know where the byte is starting and where it is ending. So, if you want to send 1 byte of data, you are going to send 10 bits of information on the serial port at this rate. And it is for 1 byte. Now, suppose if you want to send 10 bytes, you have to multiply it by 10. So, it is going to take that much of time for this whole thing to go. Now, what happens on printing the serial output is, normally it will be done on print interrupt. But what happens normally is, it is going to put it in a buffer. It is not going to wait for that to, all that to be sent across. It may be put on the buffer, okay. And then the USART, whatever USART hardware, which is interfacing with the USB interface and then sending the data out, is going to keep sending the data by reading it like a cyclic buffer. It will be sent. So, but still the processing of print is costly, okay. Print itself is going to be expensive function. It is going to, some of you, not all of you, have implemented a printf, how complex the code, so it is going to take some time, sufficient time. So if we run even this plotting information on the same core as the inference engine, it is going to use the same code for both the job. So it is not running in parallel and you are not making use of the dual core. So what I plan to do is I want to split up. I want to run this on one core, run this on another core. That is the code that I have written now. I am going to show you. So presence of two cores enables us to run them on different cores to get a maximum performance out of the hardware, because I want to see the output as fast as possible, as much as possible. I want to run the inference engine, feed the data, because you may think that it is not very urgent in my case, but if you are really running a camera image, if you are inferencing it, you will see that I want it faster, because I know if a face recognition software is running, then you want to run it fast and output it so that you can send it to the internet through Wi-Fi or whatever, through internet connection, and then take action. So you need to, inference engine has to run faster. So you need to find a way of doing it. So I am showing you the way to design your software on the ESP32 side or any other embedded hardware side. So which core to use? Okay, this is the question that I want to answer. Now we have core 0, core 1. Already while manufacturing the or designing the chip, okay, ESP32 guys did design these cores for a specific purpose. They designed this core 0 for protocols, okay, and then they designed this for application. Now you may wonder what is that they need to do to say that this core is for protocol and this core is for application. I'll tell you, both cores are identical in nature, in the sense both of them have same set of registers. They have the same core running, that extensor processor. And both of them have a floating point processor which does floating point operation. I want to explain something more maybe in the next class about that. Okay, so both of them are identical in terms of the capabilities, but they have interfaces for different things in a different way done from the hardware. It's not that I am not saying that you cannot access the Wi-Fi, okay, from here. You can do it, but there may be some performance impact. But if you use the protocol, Wi-Fi protocol running on this, and the Wi-Fi hardware is here which is connected to this, then it will be effective. Okay, so they specifically tied the Wi-Fi to protocol, this core 0. Now you are not writing the driver for Wi-Fi, so most probably what they would have done is the software which is running the Wi-Fi driver, they would have pinned it to this core. Pin means they would have made it that it should run only on this protocol core. Now suppose, imagine you are writing a code which is taking some input from the Wi-Fi, and then image is coming, and then you want to run the inference engine on the image. Now you cannot make this Wi-Fi to run on this core, because they might have already taken care of running it on only this core 0. Now what happens is, you have received the image, maybe you are storing it in a flash memory, and then you want to run the inferencing, but you are not taken care of running your inference engine on another core, and you are running it on this core only. It is not a major crime, but the problem is, when you are running the inferencing engine on this core, Wi-Fi is not going to get a chance to run, or it cannot maybe receive the image and then put it in the flash. It is going to be fighting for the core, though one core is already available which could have been used. So you need to free up the core which is meant for some purpose by using the other core based on its purpose it is made for. So if application has to be running on this, as far as we are concerned, inferencing is an application that we are running on that. So we should try to run the inference on core 0. Okay, I'm sorry, whatever. Okay, protocol 0 is core 0, right? So core 1. Okay, and then enable the core 0 for some purpose. Okay, I don't want to take the core which is not meant for my application to run. That's what I'm trying to say. So what I do, based on the priority, I want the application is higher priority, because who is producing the data, and plotting is the low priority. Please remember, the displaying is the low priority than actually processing the data. Do not mix up the priorities. Though I have given the both the tasks same priority in my code, we can change it. But because I am running it on two cores, it's no problem. I'll tell you about that. So you need to decide the priority of the task, the core on which your task is running, and based on what it is meant for, what it is designed for. So making a software efficient on an embedded platform involves not only your software skills as well as it involves the hardware skills and the OS skills put together. Okay, everything you need to know what is good for your end application. So that's why I am explaining everything. You may not get everything that you need, but at least you will get an awareness that you need to be cautious about these decisions when you are doing a software architecture of your application. So core 1 is meant for application, which is optimized for running applications, in our case inference engine. So we can choose core 0 to run data plotting and core 1 for inference engine. We need to create two tasks. Okay, I am going to create two tasks. One is plot task, other one is inference task. So I am going to run the plotting code on the plot task and inferencing engine on inference task. Now I will ask you something. Okay. Okay, let me complete this before I ask you the question. Okay, what is the time we have? Okay, I am going to be running out of the time, but at least okay, I want to cover everything that which it will be useful for you. Okay, now before I go into the difficulties of running two tasks on two cores and then conveying information between them, how do you structure it? Okay, so before that you should know a little bit about how is it being scheduled, the task running on different cores, how they are being scheduled. You need to have the OS fundamentals for it. Okay, now let me explain core 0, core 1. Okay, OS FreeRTOS, our friend, has one scheduler. Okay, functionality. Yeah, function, it's a scheduler function which will be called when one of the cores need to remove the task which is coming running currently it was running, and then bring in some other task to that. Similarly, one of the tasks running here has completed its execution or it is blocked. I need to bring another task to that. Or an interrupt has come and some task, higher priority task, has become ready now. So I need to bring that now into one of the cores, because what is running currently may be a lower priority task than the one which has become ready now. So there are many occasions where the scheduler will get activated. See, remember, scheduler is a part of OS code which gets activated on some event. Either the currently running task completes, or if there is a time quantum, it completes the time quantum. That if it is a scheduler is based on the time, maybe you run for 10 milliseconds and then schedule another task. So when the timer interrupt happens, this task will be removed and something else will be run. So, or different events can happen. Data has come and then some other task has become ready, or some higher priority task was in a delay loop. Okay, 100 millisecond delay. That time has happened, and this task which is delayed is put into the ready queue. Okay, it has put into the ready queue because 100 milliseconds elapsed. Now, whatever is running, if it is a lower priority task, this higher priority task which has become ready should be given. So it is a priority based scheduling. Okay, the FreeRTOS what is running on our ESP32 is a priority based scheduler. The lowest number priority, okay, lower number priority is low priority. Okay, high number priority is higher priority. Please don't think that it is normally this is the way it is all. Okay, it is maintained in all OSs. Different OSs follow different conventions. Do not assume that lower priority number means it's a low priority. It could be a higher priority also. Okay, you need to look at the documentation before deciding on it. Okay, it's not always there's a standard that you need to use the lower priority number for a lower priority task. So it is a convention what you are following. So scheduler is going to go with now look at the ready queues for each priority. Each priority ready queue will be maintained, which are the tasks are ready. So it will keep coming from the top looking for any task which is ready from the higher priority to the lower priority task based on whether it has to schedule it on core 0 or core 1. Because if a task which is running here has ended and something has to be brought, the scheduler is going to run to pick a task from this list for core 0. Similarly, if some task running here has ended, then the scheduler is going to run separately, picking up a task for running it on this core. Remember one thing, these two can happen simultaneously. Okay, because both cores are running simultaneously in parallel. But you may wonder, how will I access this data, which is a common data, and only single entry of single list is maintained. Don't think that there is a separate list for core 0 and core 1. No, because that is a very complex implementation. It's not even good design. Okay, there is a single design. Now, how is the mutual exclusion is taken care of? They may have some small mutex or some way of semaphores, or maybe disable the interrupt. That is the worst case. They may not do it, but they will use some critical section so that while they are handling this linked list while the scheduler is going through it. Okay, but what I am saying is the event which is asking the scheduler to look for a task can happen at the same time on both the cores. But maybe whoever comes first may finish off the job, and then the rest other fellow will come and do the rest of the job. Okay, that is how they are doing it. Now, I am going to show you how it is done inside. You may wonder, why should I know this? I don't need to know. I am writing some application. Why should I know? Remember, if you don't know what is happening underneath and how is the scheduler is picking up the task, you need to know much more than what I'm going to explain. Otherwise, what will happen is the code that you write may fail and you will not be able to even debug it and find the fix for it. Okay, it is going to be a nightmare. I'm telling you, it is not an easy job. It comes by lots of experience and breaking your head working on the hardware. So what is happening? Priority 9, priority 7, 7, 6, whatever. So for each of the priority, there are ready queues. They are all ready queues. Okay, it is already mentioned. Now, what is the coloring? Coloring is, this is the task which is this color, means that these tasks are pinned to core protocol core. Protocol core is what? Core 0, right? Core 0. So protocol core is core 0. So if you see this coloring, I will tell you that you can, when you are creating the task, you can pin it to some core. That means what I mean by pinning it to the core means that task will be run only on this core. If it is pinned to the core, even if core 1 is available, doesn't have anything to run, if it is pinned to core 1, that task will never run on this core. It will be only run on this. Similarly, something is pinned to this, will only run on this. Now, what if I don't pin it? Though so far, whatever you guys have written or whatever I have written and you have written, those tasks are not pinned to anything. That means they are free to run on any core. So what happens is scheduler may be called based on which task is getting freed up on a core. Then your task will be picked up for running. So what has happened? Maybe in the past, your tasks are not fixed to one core. So it might have run on this core for a while, and then later on it might have run on this core. Okay, it could have happened anyway. It may be running on both one after the other, not at the same time. Please don't think that the same task is running on two cores, but it could run on one and then it will come out, and then maybe next time when it is scheduled, it could have run on the other core. Now, how is it running properly? Because any time the task could have been stopped and then it may be scheduled on to run on another core. The reason is both the cores are identical. I told you that both are identical. That means inside the register, content, and whatever hardware is there, everything is identical. Not only that, the memory, whatever it is seeing, as I told you, symmetric multiprocessing, it is going to see the same memory from both the cores. It says the same memory means if this core is sending out a address 10234, it will pick one location here. Similarly, the same address is sent by this core, that will also pick address the same location. It will also pick up the content of the same location, which is not true. Which is not true in our laptop. If your laptop is having a multi-core processor, or Linux is running, or maybe our Windows 10 is running, those cores need not have to be mapped to the same way. It need not be. Okay, it could be arranged in different ways. Maybe one of the cores may be looking at the memory in a different way. So only SMP processors, if it is designed as a SMP processor, symmetric multiprocessing, then all cores will access the same location like this. So what I am trying to say, if you have different tasks which are pinned for some cores, some are not having any affinity. They are called processor affinity. The tasks do not have a processor affinity. These are the tasks which are not pinned to any core. That means if a particular core becomes ready and this is the highest priority task which is available, then it will be made to run on the whichever core available. Okay, but if it is pinned to something, it will be skipped. Suppose I will tell you, if suppose you are looking for a task for a particular core and you don't see that, so suppose assume that okay, scheduler is called for this protocol CPU. Okay, because one task which is running on protocol CPU has become ready. Sorry, it has become blocked or become dead. So it has to pick up a next task. So the scheduler is running on behalf of protocol CPU and it is looking for a task to run. Now it comes here. This is the highest priority task available in the ready queue. But unfortunately, both the tasks are pinned to app CPU. But I am looking for a protocol CPU. So I cannot pick this task and run it. So what will happen? Scheduler will skip to next priority. Now you remember, even though you have a higher priority task which is meant to run on APP CPU, is ready to run and waiting to get a CPU, it may not be picked, and a lower priority task which is priority 6, maybe this which is not even having affinity or having affinity will be picked up to run. That means it is not a strict priority scheduling happening here. It depends on whether you have pinned some application to some core, and then if that is not available, then you cannot help it. You cannot say that no, I want that. It is like a standing in a two queue. The queue you stand here normally goes slow, whereas the queue here will be moving faster. You can't jump here. Okay, once you decided that I am pinning my tasks to this, you are finished. That seems not finished, but you have to live with these problems. Okay, this fellow will get to run, who is not even worried about which core it is wanting. Okay, so that is how it is scheduled. Now, how is it implemented? Little bit I will tell you. I am not going into the details of our task here. Scheduler can be called from any of the cores based on the events on each core. The scheduler will pick the highest priority task which is eligible to run on a particular core based on whether it is pinned to a particular core or not. So it will pick up a core task based on whether it is pinned or not. If it is not pinned, then it will pick up anything. Okay, but it will go searching for a task from higher priority to low priority, and it will be looking at the ready queue only. Okay, please remember, the task which is on ready queue is ready in a sense it has all the resources for it to run except the CPU. If you know the definition of what the task which is on ready queue means, the tasks run on the ready queue have everything. That means they have all the files they want, all the data they want, and events are all, it's not waiting for any event. It's all ready to run. Problem is it doesn't have a CPU to run. Except the CPU resource, everything is available. So the scheduler is always looking for some task which is in the ready queue, which is looking for a CPU, because scheduler is looking for a task when the CPU becomes ready, or sorry, available or free. So it will look from high priority to low priority ready queue. If queue is empty or the queue is filled with all the tasks which are not meant for the CPU it is looking for, then it will go further and keep looking for. Then what if it doesn't have anything? Then only the idle task comes. Okay, idle task, there is idle task for core 1, idle task for core 0. So if nothing else is there, idle task will be picked up and it will be made to run. because CPU cannot sit idle. Either you sleep it, means you switch off the clock and make it sleep. Okay, it is also there possible. No, our ESP32 has a low power mode. Otherwise, you have to keep feeding something. So if nothing else is there, idle task will be running on the core. I hope this is clear. So how is it done, implemented? Very simple. Okay, it's not complex. Assume that priority 9 is highest priority. I have not shown anything 10 here. So this is the indication that it is the index, px index. That means a particular task has been picked up by a scheduler. Okay, so imagine a situation where this task has been picked up from the priority 9 ready queue to run on some code. Let me assume this is what app CPU, right? Okay, assume that protocol scheduler, that means what? Protocol CPU scheduler was running. It wanted to pick up some task and it started off. This is the head of the queue. Okay, head of the queue. So it saw that task A TCB is here. TCB means task control block, the task information. Now, what is that? It is scheduled. It is pinned to the protocol CPU. So very good. I will pick it up. So what does the scheduler do? It picks up this task and then say that px index is this one. That means it says that this variable, this is a scheduler variable, RTOS variable, which is now pointing at this value. Means what? In the previous run of the protocol scheduler, this task has been picked up by it, because you don't know on when the scheduler for app CPU may get a chance to run, and then that fellow also will come looking for it. So if no other higher priority tasks are running, that scheduler also will land into the same priority queue. So it should know. Okay, so that this is what was picked up earlier. Now imagine this scheduler is getting a chance to run. Then it will know that, oh, this task has been picked up. So it is a doubly linked list. It comes here and looks at this, and it knows that it is pinned to protocol CPU, whereas I am looking for a task for APP CPU. So it will skip it. It will skip it. Then it will come here. It is for me. So it will pick up this task to run and initialize the px index to this value. Now imagine this protocol scheduler has done with the previous task and it is getting chance to run. Now protocol scheduler is running now. It will start running from this task now. Now what has happened? This task B, which should have been picked up, is impacted by the scheduler of application CPU running in between. So now we can imagine, remember, there is an impact of your task getting picked up by the scheduler of another core getting a chance to run. So you need to design your application to avoid it. I don't know. I'll have time to explain it. There are some techniques you are to use. Okay, I will tell you maybe. Okay, right now it will be too much. So what will happen? This task is not picked up, though it's a higher priority which is ready and it is sitting before, because the reason that this is sitting in the same priority ahead of this task means this has become ready earlier than this. And if you ask me, in a priority wise, this task has become ready earlier than this, so you should be picked up. But the problem is scheduler meant for application CPU has run and it has skipped it. You cannot do anything. You can come later on. So what will happen is it will come here and it will pick up this guy. Now if suppose there is nothing else here, maybe it depends on the implementation of the scheduler. It may be before going further into lower priority, the scheduler might come back again and check whether anything has been skipped or not. Okay, if they have done that, then it will be an infinite loop. I don't know how the implementation is inside. So they might have even made it simple that they will go to the lower priority. So that means what? This guy is not going to get it during that time. But when the scheduler gets a chance to run again, it will come back again, and from the priority 9 it will start and it will get picked up. Don't think that it will never be picked up, but understand that there is an impact of one scheduler impacting the task picked up by other scheduler. Okay, though those two cores are running in parallel, they can impact each other. Okay, keep in mind when you write applications for ESP32. Okay, I don't know how much time I have. I have already overshot. So I cannot demonstrate it now. Looks like I need to stop it. Okay, guys, what I will do, I will take, do you have a class now? Immediately? Can I take 10 minutes? Okay, no, sir, no class. Okay, no 10 minutes, I thought. Okay, can I take 10 minutes? That is yes or no? Yes, sir. Okay. Manish Shankar will get A grade. Shogam Roy also will get A grade. Jyoti also will get A grade. Anand Jain also will get A grade. All A grade. Okay, good. Don't think that way. Okay. I'm not deciding grade based on this. Okay, I will finish off in 10 minutes. I will show you the code and explain maybe on Monday. If I want, I can share the code to you without explanation. Okay, what I have done now is, because of all these things, I have uh, done this way. Okay, now you will realize why did I taught about message queue. Okay, why did I taught earlier about which task is running on which core. All that you will understand now. I don't teach anything unless there is a connectivity between what I teach earlier and what is coming later. Okay, so what I want to do is I want to run the inference task on this CPU, because application has to run here, and I am keeping a loop task also intact. Okay, what does that do? It is going to do a blinking. Okay, its job is only to blink. Okay, maybe 1 second blink. It is very very low rate. It doesn't impact any other task. Okay, it's going to come once in a second only. So I am going to do a load so that you know that your task is running on the board, blinking something. Okay, so now what is going to happen? This inference task is having the data which is completely fed from 0 to 2 pi. If it is a full sine wave, x value is going to be fed same 1000 samples whatever we have decided earlier. So it keeps pumping the data one after the other, and then it predicts it. Output is found. Then what does it do? It sends it to the other guy. Okay, actual value, because when you are running the engine, you send the actual x value. Okay, not no, some x actual you are sent. Okay, some x value, sorry, no, there is no x actual, some x value. That means sine x value. Okay, and then our sine function is giving you y actual, and then our prediction is giving you some y predicted. Okay, so you have two values which are y prediction and y actual, which are getting generated every time. Okay, it is not generated. Yeah, I would say that it is generated. Okay, because it is, we are doing a computation using sine wave, sine function method, mathematics function, or our predicted inference engine. So you need to send both the predicted and actual y values to the message queue. Okay, now plot task will be continuously looping on this, waiting for this. Any data comes, it will plot it. Okay, then again come and sleep on the message queue. So I don't want the plot task to run continuously, so I will say that sleep on time based. You know that there is a time based wait on there. So you wait for some 2 seconds or something, which before that anyway data will come. So you wait for some time. Okay, so now which is running faster? If you ask me, the 450 megahertz is the clock. Okay, sorry, 240 megahertz. 240 megahertz is the clock of ESP32. Okay, I think it is not getting multiplied or anything internally for the CPU clock. Okay, I have not seen anywhere the data saying that. Assume that it is running at the same clock rate. Approximately one assembly instruction will be taking 4 nanosecond. If you divide by 1 by 240, okay, megahertz, you will get it around 4 nanosecond. Now I am going to choose 50, 100,000. Okay, whatever, 500,000 baud rate here. So it is effectively going to take maybe few microseconds. Okay, few microseconds to print the data. Okay, so this is actually going to be slow compared to this guy. Okay, this is little faster in the sense instruction wise, but based on the model that you have, it may take more time than this. You don't know, okay, how much of computation you are doing. But what I'm saying is faster in the sense the instruction, one assembly instruction. That doesn't mean that this whole thing will be completing in 4 nanoseconds. It is going to take much more. So what I'm trying to say is you can print it and then afford to wait on this, provided you don't take too much time in printing this. Okay, in the sense, do not choose the lowest baud rate here and then try to make the serial port getting filled, and it will overrun. Okay, it will not be plotting data. Okay, it will, what will happen is plot will come, it will not be continuous, it will be intermittent, because some data will be lost. It may not fail, but some data will be lost because you are pumping it into serial buffer and then plotting it. And if you are running it at a very low rate, your buffer will get filled up, and this guy is producing more much faster than how you are printing, so it will get overwritten. So you need to structure it such a way that you don't lose any data. At the same time, you don't run it slow also. So that is what I did. No, this is what is called tuning your application. So you need to choose a proper baud rate which is working. Okay, which is the highest baud rate I have chosen, because if you choose the highest baud rate, it is good. Okay, I'll plot whatever I have data in my hand, and then I'll come and wait for a longer time. Then the onus is on the this fellow to produce the data for me. So if it is taking more time, no problem. So producer should take more time than the consumer, in the sense consumer should not consume slower rate, in the sense, okay, I don't know that I'm showing it rightly. If execution time, okay, execution time is very slow here. Suppose consumer is slow, producer is fast. Let me say that way. If producer is fast and consumer is slow, data will be lost. Okay, so you need to plan it like that. And similarly, this fellow also should not be very fast that consumer is not able to consume. Then it will be message queue will overflow. Either message queue will overflow or the serial plot will go. I want you to think little bit deeper and then analyze what is what will cause what problems and then how to resolve it. So what I need to do was I need a maximum data, data to come. So I introduced one small delay between two predictions. Yeah, 1 millisecond delay I put. Okay, so and then I chose this. Everything was going smooth. Okay, there is no overflow here. My waveform was continuous. I will show you how it is running, and it is running for smoothly forever. Okay, so that is the tuning you need to do, and it doesn't come easily. You have to really struggle to find out, debug it yourself and find out. So you need to think all this background knowledge you have to have, so that you get a better idea of what is happening. So with this, both plot and inference tasks run in parallel on both core. Plotting speed, the baud rate, can be increased so that message queue does not overflow, as well as serial port. Okay, because of the producer inference task giving out data faster than the rate at which the plot task can consume. Okay, most likely maybe I should replace it with the serial plot. Okay, maybe yeah, I don't know, it depends on how this serial plot data is consumed. Okay, if the plot task is waiting for the data to be fleshed out, then message queue will be overflowing. If it is doesn't wait, it just, even if it is overflowing, it just pump the data, then message queue will not overflow, but serial port may overflow. It needs to be studied. Okay, it's more involved. Again we have to dig deeper into it to see. So increase the baud rate to maximum what is possible. What I did, I increased it to 1 lakh also, or sorry, 10 lakh. Okay, sorry, yeah, 10 lakh. But still it was not working at all. It was very, you can try to do it. Okay, reduce it, increase it, all that you can do. Whatever I did, you can also do. So pin the plot on the inference task on respective course, and everything will be smooth. Okay, that's what is the theory part of what I wanted to show you. So let me just show you the output and then stop. If you want me to share the code, I can do it, so not a problem. You can look at it. Okay, so this code maybe I will show you running. So if you see that I have defined the plot, so it is for the plotting purpose I am compiling it for. So it will be nice if I open the plotter. So this is what I see. Okay, so full sine wave. Model is all there, 16 by 16. Okay, both 16 layers. Epox is 900. Batch size is 16. This is what I have built it for the model, and you can see that actual predicted and the zero line, everything is coming fine. Okay, I have amplified the output to 3. That's why you see that it is fluctuating or changing between -3 to 3. So this is the plot output. Okay, and you can see that it is really running faster than what we saw earlier, because we are running it on 2 cores and we have a higher baud rate also. You can see that baud rate what I chose is where is it, 500,000. Okay, baud rate is chosen. Now let us see what happens when I choose a plotter on building the application and monitor I see. This is what you see, because these are the output coming out continuously, and this is what you will see if you open a monitor. So this is not meant for that. Now suppose I don't know, I am not interested in plotting, then I comment off this. Okay, I am doing it because you can also do it if I share the code with you. So now I want it for monitor. So let me see. Now if I show the plot, because we are always interested in knowing what happens when you choose the wrong thing, right? That normally we do. When the wet paint is there, we touch it to see whether it is really wet. So now you see it's totally useless. Okay, don't try to even look at this value and then think that something is not working. Now monitor, if you see, this is what I am doing. I am running on this. This is the X value, actual value, predicted value. Every 1 second I am printing it. So maybe the values are more or less same, actual and predicted, but there will be difference because the waveform is not exactly same as what actual value is. Okay, this is how you debug it. Okay, so you can choose one of them, you can write the code accordingly and do it. Okay, I will explain about the stack size maybe on Monday. Okay, any questions before I drop off? I will take the attendance, that is most important. You guys are hanging around for one question I have, do you want me to share this code or defer it till Monday? I am okay for both. Anyway, I'm not going to look into it. You share whenever you want. I can hear you guys saying. I don't know. Oh, sorry, I'm going somewhere. Where is agreement? Oh, okay, attendance. Share. Huh? Okay. I don't know whether you will see it or not, but I will share. Okay, guys. Thanks for staying late. 20 minutes. Bye bye. See you on Monday. I hope Monday is not a holiday again. I will complete it on Monday. Then we will take on classification task on Tuesday. Okay. We will take up a small classification program, how to port it onto ESP32. Okay. It's something like cars, getting a data of cars based on the parameters of cars, whether it is acceptable or not acceptable, useful, good or very good, something like that, classification engine. That we will try to understand, developing it on Python and then porting it onto ESP32. I don't know whether we can do it on the same day, but that is the plan for the next week. Bye bye. Have a nice week.